In this video, we're going to talk about the idea of mathematical induction and how it can be used to verify arguments that we want to make. And this could be used in computer programming. This could be used in any situation in which, first of all, there are too many cases to prove, and when contradiction would prove to be equally difficult. So in a situation like there are infinitely many primes, induction wouldn't work very well, but contradiction would, because supposing that there aren't infinitely many primes and showing that there's one more prime beyond the finite number of primes that you claim there are is a way to do contradiction. But there are situations where this is not possible. So the logic behind method of induction is that first, step one, we want to show that the argument is true for the base case, whatever that might be, n equals 1, or whatever value is claimed to be the first value for which the argument is true. Assume, the step two, that the argument holds for some arbitrary case. And finally, the inductive step is use this assumption from step two to show that the argument holds for the next case, n equals k plus 1. And the idea is this. We've got dominoes stacked up, and we want to tip one of them over in that old fun game where we could tip one over and that would tip the next domino over, which would tip the next domino over, etc. We kind of want to use this argument. So if n equals 1 is the base case, n equals 2, n equals 3, and so on, and we want to kind of show that this holds for all of these dominoes, that basically, where do we stop is the question. Because if this is, infinitely many of them, then it would be very hard to show that the argument holds for all of those cases. So we show that, first of all, between these two steps, we kind of just assume there's one domino somewhere in here. Doesn't matter where, I'm really just picking kind of an arbitrary spot. But such that if I assume for n equals k that it holds true, and I show that based upon that I can make an argument that k plus 1 is also a true statement, then that arbitrary reasoning here shows me essentially that if I knock down one domino, regardless of which one it is, it will knock down the next one. Okay, so that's what these two steps show me I can do, that knocking down a domino automatically knocks down the next one. The first one shows me that I've got to start somewhere. So if I know that every domino knocks down the next domino, and I start with n equals 1, then that will tip over n equals 2, n equals 3, n equals 4, and so on. Okay, so to actually implement this, this is the idea. Since any domino k knocks down domino k plus 1, the next domino in the sequence, that is, any domino will always knock down the next one. Then by knocking down the first domino, the second domino falls. Knocking down the third domino, which knocks down the fourth domino, which blah, 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 blah. Forever and ever and ever, we can continue to cover all our cases that way. We can't just show that if it holds for case 1, it holds for case 2, because that only proves that it shows truthfulness for the first two arguments, but it says nothing about the further arguments. This generalizable set of steps, the inductive reasoning here, is really what makes this work for all values of n. Okay, so let's suppose that we want to develop a formula, first of all, and we wish to sum the first n whole numbers. So we have some sort of maybe computer algorithm that we want to add up, and we want to know, first of all, is there a formula that we see for this process? Okay, so what we're thinking here is, let's just draw a table, and what we want to do is we want to look at the first n whole numbers and then look at the sum of those first n whole numbers. And the way I'm going to write that is using summation notation, and I'm going to sum the elements that we'll call I, starting at 1, ending at n. And so I'm going to add up all of those elements. So this formula, this is a way to say add up basically all integers starting at 1 all the way up to and including the last value, which is specified by these are just indices. This is the indexing variable. So each time you take, I is 1, and you add that to the next index, which is I equals 2, you add that to the next index, and you do this basically n times. So another way of writing this out is this compact notation. So let's just take a look at what would happen if I just took the first, the first whole number. Well, that's just the number 1, and that's not being added to anything, so that's just 1. If I take the first two whole numbers, now I'm adding 1 plus 2, which gives me 3. And if I take the sum of the first three whole numbers, that's 1 plus 2 plus 3, so that gives me 6. And if I add up the first four numbers, well, that's just going to be 6 plus 4 more, which is 10. And then adding up the first 5 whole numbers, that's just the sum of the first 4 plus the 5th one, which is 15. Now, if we kind of study the relationship between n and the sum of those n values, what we notice is that, first of all, I don't see any way to get directly from a function of n to get the sum. But if I do enough playing around with this, I can see that if I take the current value of n, which is 1, for example, and I add to it n plus 1, which would give me 1 times 2, and I divide that by 2, I will get exactly the sum. So for example, notice that if n is 2, 2 times 2 plus 1 is 3, 2 times 3 is 6, divided by 2 is 3. 3, if I want to sum the first 3 numbers, 3 times 4 is 12, divided by 2 is 6. So this seems to be a quicker way to get these summed values rather than actually having to go through the iteration of adding each time. So now, normally at this point we'd say, well, we think we have a relationship. We think that instead of having to manually add those numbers, I could just figure out how many numbers I'm adding, take that number, multiply it by 1 more than that number, divide it by 2, and I would be able to get those sums without actually physically adding. Well, now my question is this always going to be true? This is a proposition at this point. The sum of the first n natural numbers starting at 1 all the way up to that nth value is simply where I'm going to stop, that value, n divided by n plus 1 divided by 2, or n times n plus 1 divided by 2. Now my proof has to cover all the cases, right? So I have to do case 1, or step 1. And step 1 says we're going to show it for the base case. So show equality true for n equals 1. Okay, so what I'm going to do is I'm going to evaluate this side, I'm going to evaluate this side, and make sure I get the same number. So the sum of all values from 1 to 1 of I is just equal to 1, right? Because I'm just adding a number to no other number. And then I'm also going to evaluate this side and see if I get the same answer. So 1 times 1 plus 1 divided by 2, well, that's 2 over 2, which is 1. And I see I get the same answer. Therefore, formula true for base case. Alright, and so then the next thing I want to check is, or the next thing I'm going to do is I'm going to lead myself up to the inductive step, right? I don't want to keep trying this over and over again for different cases because I'm wasting my time. I don't know that it's going to actually work all the way up to the infinitude of all possible numbers. So I'm going to assume formula holds for n equals k. So what does that mean? Well, that means that the sum from I equals 1 up to k of the integers from 1 to k is going to equal, well, if I stop at k, then that means my formula should be k times k plus 1 over 2, based on observing that pattern. And now my inductive step. My inductive step is going to be prove that this is true. By this, I mean the formula is true for n equals k plus 1. Okay, so that is what I want to show, is that if I sum from 1 to k plus 1 of all the natural numbers, that what I will get is, okay, so that means that I should plug in k plus 1 times k plus 1 plus 1. So what I'm replacing is so in our formula, the n's get replaced with k plus 1, right? Because my ending index is k plus 1, so that means all of both of these n's should be k plus 1 as well. So if I divide all of that by 2, I'm going to simplify this just a little bit. That should come out to k plus 1 times k plus 2 over 2. And now what I need to do is, wow, my pen keeps spiking, I'm not sure why. I need to show that, in fact, that if I add up those natural numbers, I'm going to get k plus 1 times k plus 2 over 2. Okay, so first of all, I'm going to operate on this side, and what I'm going to do is I'm going to try to break it up so that I can use my assumption from the previous step. Okay, So let's think about this for a second. So summing the first k plus 1 natural numbers, that means I'm going to add 1 plus 2 plus 3 plus dot 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 all the way up to k, and I'm going to add the k plus 1 integer to that value. So what I'm going to do here, one of the tricks is to first of all observe that right there, that's the sum from I equals 1 to k of I. And then we're adding to that the k plus 1th integer. Well, the reason I did that is because I want to try to get my formula to be in terms of what I already know. So that means that if I can split this up into the sum from I equals 1, I equals, this is not going to cooperate with me, I equals 1 to k of I, and I add to that k plus 1, that gives me the same thing as that right there. And I'm not doing anything with the right-hand side yet, because what I'm going to do next is I'm going to move my way. I'm going to insert a new slide here. I think I am. Okay, so basically I now know that I have the sum from I equals 1 to k of I plus the k plus 1 term. All right, and I still want to show that that's going to give me k plus 1 times k plus 2 over 2. So what I'm going to do now is because from my step 2, I know that right there by assumption will lead to k times k plus 1. So I'm making a substitution now. This is all just algebraic. K times k plus 1 over 2. This is by step 2. Plus k plus 1. Now I'm trying to get to see if that gives me the same as what I would expect it to give me. And so I'm going to do a little bit of surgery on this. I'm going to get a common denominator here, just because I want my end result to be over 2. So if I multiply this by 2 over 2, I get 2 times k plus 1 over 2. Still the same fraction, but now I can add these together, and that gives me, well, first of all, what I see here is that both of these terms involve a k plus 1. So I can factor out a k plus 1 term from both of those, and then what I'm left with is k plus 2. So I've factored out this term here, I factored out this term here from the numerator, and I have k plus 1 times k plus 2 over 2, which gives me the same answer as what I was expecting. Therefore, by induction, it is true that the sum of from I equals 1 to n of the integers is equal to n times n plus 1 over 2. So what I've been able to accomplish is basically that if I ever want to add up a series of sequential integers starting from 1 to n, I know that I don't have to do it manually, that this formula, I can rest assured that this formula will do the summation for me. And from a computer programming standpoint, if you are doing repetitive things like this, like doing a bunch of for loops where you're just adding a bunch of stuff together, the question to ask ourselves is there a faster way? And if you think there's a faster way, then you can always check to see if that way will always work by using induction. So anywhere where there are for loops, this is a useful type of approach. In the next video, we'll take a look at one more example of induction, and then we'll call it good.